Ever found yourself pondering how multiple processes or threads share common resources without stepping on each other's toes? Well, that's the essence of the critical section problem, a pivotal concept in computer science and concurrent programming. Imagine a bustling city intersection, with vehicles representing threads or processes, and the intersection itself being the shared resource. Without proper traffic management, there could be accidents, traffic jams, and utter chaos. Similarly, in a computer program, when multiple processes or threads need to access or modify shared data, they must do so without interfering with each other to avoid conflicts, data corruption, or inconsistent results. This is the crux of the critical section problem. But what makes a portion of a program a critical section? It's the part where a process or thread requires exclusive access, much like a vehicle needing to pass through the intersection without colliding with others. When multiple processes or threads vie for exclusive access to shared resources, the critical section problem emerges. It's a bit like a dance, where each dancer must be aware of their space and the movements of others to avoid stepping on each other's toes. In concurrent programming, this dance takes place when threads or processes synchronize their access to shared resources, ensuring that only one can access or modify the data at a time, while others wait their turn. The critical section problem is not just an abstract concept. It's a practical issue that programmers grapple with daily when designing systems where multiple threads or processes interact with shared resources. It's a bit like choreographing a dance to ensure that everyone moves in harmony without bumping into each other or causing disruptions. Now that we know what the critical section problem is, let's delve into its key characteristics. Understanding the critical section problem requires grasping three essential characteristics. First up, we have mutual exclusion. This characteristic ensures that only one process or thread can be in the critical section at any given time. Think of it as an exclusive VIP lounge at a club. Only one process gets the VIP treatment, having full access to the shared resources, while all others must wait their turn. This exclusivity is crucial to prevent conflicts, data corruption, or inconsistent results. Next on the list is progress. This characteristic is all about fairness. If no process or thread is currently in the critical section and others are waiting in line, one of them should be allowed to enter within a finite amount of time. It's like waiting at a traffic light. Even if it's red now, you know that eventually it will turn green and you'll get to move forward. Progress ensures that no process or thread is left waiting indefinitely. Lastly, we have bounded waiting. This characteristic sets a limit on the number of times other processes or threads can enter their critical sections before a waiting process gets its turn. Imagine a queue at a coffee shop where a new customer can't jump the line. This prevents a situation called starvation, where a process or thread is perpetually denied access while others repeatedly enter their critical sections. These three characteristics, mutual exclusion, progress, and bounded waiting, are the pillars of the critical section problem. They guide the design of various algorithms and mechanisms to effectively manage shared resources in concurrent programming. Understanding these characteristics is not just about grasping the problem, it's about appreciating the delicate balance needed in managing shared resources in a multi-threaded environment. Having learned the characteristics of the critical section problem, we can now explore some common solutions. There are several ways to tackle the critical section problem, each with its own unique approach. Let's delve into them. First up, we have locks. These are straightforward tools that control access to shared resources. Mutexes or mutual exclusions are a type of lock that allows only one process or thread to enter the critical section at a time. Then we have spin locks, which are locks where a thread repeatedly checks if the lock is available. Spin locks are commonly used in situations where the lock holding time is short. Next on the list are semaphores. These are a bit more complex than locks. A semaphore maintains a count, allowing a specified number of processes or threads to enter the critical section. This provides a greater degree of control compared to locks. Monitors come next. They are high-level abstractions that manage access to shared resources. Monitors combine data encapsulation with synchronization methods to ensure that only one process or thread can access the shared resource at a time. Following monitors, we have condition variables. These are used in combination with locks to coordinate threads based on specific conditions. They provide a way for threads to wait until certain conditions are met before proceeding. Then there are atomic operations. These are low-level primitives that ensure operations are completed without interruption. Atomic operations provide a building block for synchronization, providing a guarantee that once an operation begins, it will complete without being interrupted by another process. Read-write locks are another solution. These locks allow multiple readers or a single writer, providing flexibility for operations where read operations are more frequent than write operations. Last but not least, we have Peterson's algorithm and Decker's algorithm. These are software-based solutions for mutual exclusion in critical sections. Peterson's algorithm is a straightforward solution that uses flag and turn variables to control access to the critical section. Decker's algorithm, on the other hand, is an early solution for mutual exclusion in concurrent programming. It makes use of a pair of flags and a turn variable to control access to the critical section. While these solutions are quite technical, they find practical applications in many areas of computing. From operating systems where they manage process and thread synchronization, to databases where they ensure data consistency during transactions, these solutions are essential. They are even used in web servers to manage concurrent requests and resource access, and in real-time systems where timing and resource sharing are critical. So as you can see, the solutions to the critical section problem are not only diverse but also versatile. They cater to a wide range of scenarios and requirements, ensuring that our multi-threaded and concurrent programs run smoothly and efficiently. The next time you're dealing with shared resources in your code, remember these solutions. They might just save your day. The solutions to the critical section problem aren't just theoretical. They're put to work in real-world scenarios every day. In the realm of operating systems, solutions to the critical section problem are fundamental. They help manage process and thread synchronization, ensuring that tasks are performed without interruption and in the correct order. For instance, when you're multitasking on your computer, running several applications at once, these solutions are quietly ensuring processes don't trip over each other while accessing shared resources. In databases, these solutions ensure data consistency during transactions. Imagine an online banking scenario where two users simultaneously attempt to withdraw money from the same account. Solutions to the critical section problem help avoid a race condition, ensuring that the account balance is accurate and preventing overdrawn accounts. Web servers also put these solutions to good use, with potentially thousands of users making concurrent requests and accessing shared resources. It's crucial to manage access effectively. If a web page is being updated while users are trying to load it, solutions to the critical section problem make sure users don't end up with a half-updated, inconsistent page. And let's not forget real-time systems, where timing and resource sharing are paramount. Think about air traffic control systems, where multiple radar stations need to access and update shared data about aircraft positions. In such a critical context, solutions to the critical section problem ensure that all updates are timely and accurate, preventing catastrophic errors. But let's take it a step further. Even in multiplayer online games, these solutions are at play, managing player actions and game states. Whether it's ensuring that a player's action is correctly reflected in the game or coordinating real-time interactions between players, these solutions help deliver a seamless gaming experience. In all these instances, the principles of mutual exclusion, progress, and bounded waiting are applied to maintain order, prevent conflicts, and ensure the integrity of shared data. It's an intricate dance of processes and threads, all choreographed to avoid the critical section problem. So next time you use a computer, remember the intricate dance of processes and threads, all choreographed to avoid the critical section problem. The critical section problem might seem daunting, but understanding it is crucial for anyone venturing into concurrent programming. It's all about managing access to shared resources in a way that prevents interference and inconsistencies. The key characteristics to remember are mutual exclusion, progress, and bounded waiting. There's a myriad of solutions available to tackle this problem, from locks like mutexes and spin locks to semaphores, monitors, and condition variables. Don't forget about atomic operations and read-write locks. And of course, there's software-based solutions like Peterson's and Decker's algorithms. The practical applications of these solutions are widespread. Operating systems, databases, web servers, and real-time systems all use these concepts to ensure smooth operation and data integrity. And there you have it, a succinct overview of the critical section problem. Until next time, keep exploring the fascinating world of computer science.